Okay, good morning. I will start the class. I hope we will not have any interruption now. I got connected to a stable server. So we are going to start a new course. The title is Fundamentals of Spatial Statistics. What we do in this course, the course content, we are going to look at the spatial statistics concepts. What makes spatial data analysis different from the other statistical analysis that we normally do. Understanding of the paradigms in spatial data analysis. So we have a different approach when it comes to the statistics related to spatial data, due to the nature of spatial data being location referenced. So we take into account the relative locations as well. And we look at the natural variability and how Can you all hear me?
Yes, sir.
Yes, sir.
Did you hear what I explained so far in the content of the course? Yes or no? I was not sure about the connection again. Okay, the course. Sorry?
Please repeat it again, sir.
Right. So the content of the course, we start with the concepts related to spatial statistics, with the introduction to spatial statistics. What makes spatial data analysis different from the other data analysis that you are doing in statistics? Why the spatial statistics are different? So what are the different paradigms in the spatial data analysis? And how we explain the natural variability or nature through the spatial statistics. And then we cover, perhaps we'll put this one a little bit later, spatial statistics and spatial data analysis, spatial data quality, data errors, univariate spatial statistics, and spatial data problems. Then we'll take spatial distribution of aerial data, interpolation algorithms, variogram analysis, and kriging. And then we have, we learn in the spatial data when it comes to the vector data. The new people would have not learned so far, but vector data will have points, lines, and areas. And raster data, we have the raster cells or grid cells or pixels. So whether it is a point or whether it's a area, we can do certain analysis. So point pattern analysis is something which is unique in spatial statistics, assessing whether a pattern of locations is clustered, spatial point processors, nearest neighbor statistics, second order, first order, we do second order statistics, bivariate and space time point patterns. And then we have spatial autocorrelation analysis, descriptive statistics for spatial autocorrelation, constructing spatial weights, visualizing spatial autocorrelation, local indicators of spatial association, multivariate spatial correlation. Then we touch upon spatial sampling, and the course, we have two textbooks recommended for reading. One is elementary statistics for geographers, but it not only for geographers, for giving the very basics of statistics for everybody. James Ebert and Gerald M. Barber. And then the other book is which I have authored with Mr. Gunasena, Spatial Statistics Theory and Applications. And the Spatial Statistics Theory and Application is available in the library as well. If anybody want to borrow a book, I don't have enough copies to give. Earlier I used to give it free, but now I don't have free copies available, but I can give you a few books for you to borrow and share and return to me at the end of the course. Well, the examination is mid-semester 20%, end semester 40%, and then tutorial and assignments 40%. That's how the course is structured. So spatial statistics, SS stands for spatial statistics, is an area of study which has developed out of real world problems. So when we see some problems in the real world and these problems cannot be resolved with the normal statistical methods, we had to develop spatial statistical approaches. Now, if you look at the basic statistics, the course which you have followed or which you have been following now, I think most of you have followed that course because it's a prerequisite. We have statistics under two main areas. One is descriptive statistics, other one is inferential statistics. Descriptive statistics and inferential statistics. Descriptive statistics will try to explain a set of data, large maybe, with some descriptions about that data. Inferential statistics is extract some of the characteristics of the data and predict some of the values, infer some of the values to give an idea about the process phenomena that you are studying. So bottle number 1, 2, 3, 4, 5, 6, whatever bottle number, and then the amount of water in that bottle. So you identify the bottle in terms of a number, and then you identify the amount by having the number of millimeters of the content. But when it comes to a map product, it is different, because now to identify a bottle, you have a bottle number, but here identify a location, you have two coordinates. If you drop one coordinate, it can be any point. If you drop X coordinate, if you have only Y coordinate, it can be any X value on that Y equals whatever the number line. So therefore, we need to have two coordinates X and Y, and also then what is there, like how many milliliters in a bottle, like what is there. So if you want to compare two maps, we cannot use the normal techniques. We cannot use normal statistics. We need to go for spatial statistics. In spatial statistics, we try to find answers how similar these two maps are, or how different these two maps are. Like if you have a land use map of 1960, 1970, 1980, 1990, 2000, 2010, 2020, right? You can see how these changes have taken place, how similar these maps are, how different these maps are. If you compare with 1960 map with 1970 map, how similar these are? What are the land use categories which are not changed? What are the land use categories which have changed significantly? So you can do a map comparison by using spatial statistical techniques. Or two people produce same map. So land use maps are produced by two different people. We want to see both are correct, whether these both maps are correct. We can see a similarity test, how similar these two maps are. We can check using spatial statistical techniques. And also, when we have the data, say for example, we have rainfall data. We have rainfall data, but we don't have rainfall data for each and every place. But in a catchment, we need aerial rainfall, not point rainfall. So we need to go through a process called interpolation. We need to go through a process of interpolation. It's not normal interpolation, it's a spatial interpolation. Spatial interpolation has different approach than normal interpolation. Because spatial interpolation is for area, not for linear interpolation. It's not linear interpolation. So you need other techniques. Then you have produce a map using remote sensing techniques and GIS. You produce a map. And you want to see how accurate this map is. You compare that with the real world. That also needs some statistical approaches. We learn those statistical approaches. We do sampling. Why do we do sampling? We cannot cover the entire population. When we cannot cover the entire population, we take a representative sample. We use different techniques in getting a representative sample. Different techniques. Now, if you want to do a survey of people's choice on, say, TV channel, which channel they prefer. You do a survey. You select sample and do a survey and interpolate the results to the entire country and say this is the approach. But when it comes to spatial data, the interpolation is not a linear interpolation on one direction. It is an aerial interpolation. You need to interpolate an area. So there are special techniques for aerial interpolation that we need to learn. And in normal statistics, so these are some of the areas which we'll be looking at in this course. And in normal statistics, we estimate various parameters. Starting with the basics, we estimate mean, we estimate variance, we estimate standard deviation, we estimate standard error, we estimate the confidence intervals, we estimate the skewness of the data. So we use various statistics. We have similar statistics in spatial statistics as well. But instead of mean, we use mean center. Instead of standard deviation, we use standard distance. So there are similarities, but concepts are different. We look at concepts differently. So some of the basic introduction may be a bit boring. I will go through quickly. So, and another area which we look at is spatial correlation, which we don't have in normal statistics. And the very basic theory of spatial correlation is taught by the nature. By the nature. What is that basic concept in nature that you use for spatial statistics regarding the spatial correlation? The concept is things which are nearby are similar than things which are far apart. Things which are nearby are similar than those which are far apart. What do you understand by this concept? In nature, things in the surrounding are going to be more or less similar than things that you find in a distance. That you find in a distance. It is true now if you look at the vegetation in Kandy, in Peradini, vegetation is more or less similar. If you go far distance, if you go to dry zone side, you find different types of vegetation, different nature of vegetation. So that's the theory that is taught by the nature. Things which are nearby are similar. People also, there's a similar saying. People with similar mentalities, like-minded people, get together very well. For example, it says, birds of similar feathers flock together. Right? So if you are a criminal, you associate with the criminals. It's a nature. So we can look at this kind of a spatial correlation how things are correlated in space. It's useful for us to understand the nature. It is useful for us to understand the nature because natural phenomena are also behaving in the same way. With rainfall here and 100 meters away is more or less same than the rainfall in 5 kilometers away. Right? So natural processes are also following this kind of a spatial correlated approach. Spatial correlated approach. Therefore, it is very pertinent, very relevant for us to learn this process. See how things are correlated in space. What is the advantage of finding spatial correlation? If you know how it is correlated, you don't need to measure it. You can use the correlation to estimate it. In nature, some of the phenomena are very difficult to measure. Especially this becomes very serious when you have too many places where you want to measure. Right? I will give you an example. A river flow, a flow in a river. Can you measure it? Yes, you can. There are flow meters to measure. But I ask you, measure the river flow in Mahavali River under Peradeniya Bridge. Okay. So you grew as a group, you go to Peradeniya Bridge and measure the flow. And you bring the data. Then I will say, no, no, no. Not Peradeniya Bridge. What I mean is this bridge in Gannaruwa. Now, Gannaruwa bridge, the amount of water passing through it is different to Peradeniya Bridge. So if you change the place, you have to go and measure it again. Because there are so many other substreams coming and joining the river. So the flow is different. Now, this makes measurement very difficult. That is why we try to estimate things. When you try to estimate things, we use correlations. Things which are spatially distributed, we look at spatial correlation. Therefore, it is important for us to learn how things are spatially correlated. So this is what I told you. I took the example from this crazy, but this is been found long time ago, not 1991. Not most spatial statistical methods operate on the premise that data collected over region in space found more close together are more or highly correlated with each other than points further apart. So spatial correlation is a concept. It is very useful. It is very useful. So underlying spatial statistics and spatial modeling is a coordinate space that enables measurements of distances and bearings between points according to formulas and functions. So we get the directions, we get the distances, and then try to calculate values, estimate values based on the spatial correlations. So this is what we don't cover under normal statistics. We don't cover under normal statistics. The model of space, modeling of a coordinate space, is known as Euclidean space. Anybody knows what Euclidean space is? Anybody? What is Euclidean space?
Straight line distance.
Straight line distances. Okay. Now, now if you go on the ground, we cannot use the straight line distances. We say the straight line distances as aerial distances. It's a wrong word to use, but we use aerial distances. Why we call aerial distances? Why we call it aerial? If you travel by air, that is a straight line. Is it true? Aerial distance is a straight line distance. Is it true that planes travel on the aerial distance, although vehicle cannot travel? No, that is not true. Okay, take the example of a flight leaving the North Pole to go to South Pole. What is the aerial distance? Can the plane travel along the aerial distance line? Then it has to go inside the Earth, right? If you take the globe, North Pole to South Pole, straight line is through the Earth, not air, right? But if you take Sri Lanka, if somebody want to go from Colombo to, say, Kandy, can he fly and say this is the aerial distance? Yes, can. Airplane never travels on the aerial distance. It cannot, because it has to go up and then travel and come back. So it is not the straight line distance. Do you understand the point? So although we say the Euclidean distance is the aerial distance, how the plane travels. Not really true. But the Euclidean space is defined as a space which can be connected by straight lines without any impediments or barriers. And also, when you look at variables which are distributed in space, we call these variables as a regionalized variable. Any variable distributed in space is said to be regionalized. Example, price of gold in the market. The price of gold in the global markets are not same. In India, gold is more expensive than what we find in Sri Lanka. That's why people try to smuggle gold to India. So market is a single place. You don't look at the location of the market. But if you look at the spatial distributed regionalized variables, it is important for us to understand how these changes, how these are varying, mostly when it comes to natural phenomena, how things are varying. It is important. We are trying to study those in spatial statistics. And also we have a part of error analysis. We produce maps using GIS, using remote sensing data. But all these maps are 100% accurate? No, not 100% accurate. There are errors associated with the data. There are errors which will be added during the processing. There are errors which can happen due to some kind of procedures that you adopt. Or it can be due to the production. There may be errors. How do you compare and assess the accuracy of a map? This map is 99% accurate. This map is 70% accurate. That we also learn in spatial statistics. So if you look at the gold market, which is single dimension versus monthly rainfall. You have rains, you have months. And then ozone concentration in atmosphere, which has a 3 dimension, height, length, and width. So random function is a function which operates random by pure chance. When you talk about statistics, we talk about randomness. We talk about randomness. The processes are not always random. Although we think these are random, it's not random. Now, rainfall today is a random event? No, not at all. It's a function of rainfall yesterday. Yesterday's rainfall explained part of the rainfall today. If you toss a coin and ask head or tail, is it random? Is it random? Yes, it is random, provided the coin has equal sides. That's the random process. The temperature today is random? No. There are so many factors which can determine the temperature now. So it's not random. So random process is having probability to happen whatever the outcome. So it's called random. But then if it is not random, say if it is totally random, you have 50% chance of having that. And then the previous process will not have any impact. Toss a coin, but your outcome will not depend on what happened previously. What happened previously is independent from what is happening now. There's no history associated with the occurrence of the event. But then not all processes are random. Random means any outcome can occur with equal chances. Now, if you throw a dice, whether you get 3, 6, 9, 12, 15, or 18, it's random. You can have any outcome, and having any outcome is having equal chance of happening. So it's a random. But there are certain things which is not random, but has got some statistical estimations. It's 75% probability, 80%, 90%, 99% probability. So it's not random, but it has, you can evaluate through the statistics the chances of happening that. It's not 50-50. It's not 50-50. Now, tomorrow, will it rain? You can say yes. There's a 75% probability that you will receive more than 100 millimeters of rainfall tomorrow. Look at my statement again. There's 90% probability that you will get more than 100 millimeters of rainfall tomorrow. So what does it say? 90% chance is there for you to have rainfall more than 100 millimeters. So what is the chance of getting rainfall less than 100 millimeters or equal to 100 millimeters? Is 10%. But if you ask the question, what is the chance of having rain tomorrow? Not rainfall more than 100 millimeters. What is the probability of having rain tomorrow? It will say 99.999 probable that it will rain tomorrow. Some people use this word in a wrong sense. I'm 99.9% sure it will happen. What do you say? There is a very high chance of happening that. Some people say, I'm 100% sure it will happen tomorrow. No, you cannot say that because everything is having some component of uncertainty. That's a component called uncertainty. So you need to find some space for this uncertainty to be accommodated in the analysis. So geostatistical data is data from a random process, and the randomness can be evaluated. For example, in a lake, you measure the temperature. It's not same everywhere. The entire surface area is different, and from surface to bottom is also different. So if you want to model the temperature profile in a lake, okay, or magnesium concentration in a lake, you need to look at different places, different depths to get the data. At least if you look at the surface temperature, you need to see how things are varying. What kind of random process or what kind of probabilistic process which operate on the surface to give you different temperature values. This will be important. So geostatistical data are very useful for us. Now, when it comes to spatial analysis, we use a lot of techniques borrowed from the normal statistics. For example, if you look at the linear interpolation, I'm sure most of you are familiar with. If you have known point with 20, known point of 0, and the midpoint between these two, if you interpolate linearly, we'll have value 10. So, and then what you can do is you can mark linearly from 0 to 20. You can calibrate the distance. At any distance, you know what the value is. Right? So you can get, if it is 20 kilometers away from the blue one, you can have every kilometer measured and then interpolate the value. Or you can interpolate for every 100 meters, every 10 meters, every meter, every centimeter, depending on your requirement. It's called linear interpolation. But in space, when you use a map, you can't interpolate only linearly. You have to interpolate area-wise. You have to interpolate through area. Right. To summarize the spatial data that we'll be using, we use conventional descriptive statistics to describe the data. Describe the data using statistics, we use descriptive statistics. And also we use new techniques developed for exploratory data analysis. You explore the data. You extract some of the characteristics of the data. We'll come into these examples later. So we use spatial analysis rather than data analysis. We use spatial analysis to identify spatial distribution of the variable. Normally we do data analysis. If you take the data, you analyze the data. You get the descriptive statistics of the data. You also get the exploratory data analysis to extract certain amount of information from the data. Now, when it comes to spatial description of data, which include how can we describe a map of some variable in an efficient, precise, and simplified way. So you have a map of particular variable which is changing. So when you want to give this variable, rather than giving points where the values are, we need to give a surface. we need to give a surface. If you think of elevation, we have different elevation values. So if you vertically put the elevation in a model as a height, and then you have different heights. So if you put a surface, if you spread a piece of cloth as a surface, it goes at different shapes at different heights, right? And then the shape of that surface, if you can explain by using some kind of equation, that explains how the values are distributed. Very simple. The process is not very simple, but it's simple to understand. Right? So when you can do that, you can find where the high values, where the low values, where the moderate values, where the values are changing with time quickly, where the values are stable. Is a variable evenly distributed across the map or concentrated in a single or smaller number of locations? For example, you want to study a particular plant. Say we have an invasive plant, which is going to be very dangerous. So you want to see, is this plant is distributed evenly or it's only in certain concentrated areas? So you put the data onto a map. Like recently we had this disease for pigs, and pigs die. So look at where the problem is. Identify the area which is affected. Whether other areas have reported the cases. So if it is identified as a map or as a surface, then you can take corrective actions immediately. Okay, you will find that this is an area which is spreading the disease. You can cover that area and block so that disease will not spread into other areas. Is there any pattern, or is the map in any sense random? So whether there's a pattern of distribution or it is totally random, you have no way of explaining how things happen. Only God knows, people say. When you cannot explain, only God knows. If you ask, when I toss a coin, can you say the outcome? It's random in all sense. You cannot predict it. It can be either head or it can be tail. Nobody can tell that. Nobody can tell that. Right. We'll take a quick 2-minute break. I'll start, just have a cup of water and then glass of water, I'll come back. Okay. Commonly used representations of spatial data. We use aerial data, we use point data, we a lot of analysis for point data. It's separate subject called point data analysis. We have network data. Network data is data with connectivity, and directional data with directions. So when you have aerial data, it includes observations for aerial subdivisions of a region. For example, if you take a district map of Sri Lanka and put the population into it, district population map of Sri Lanka, that's aerial data, although people are not spread aerially. So for each aerial subdivision, we have a value. We call these maps as a choroplete map. Choro means color. Plete is plated. So different color plated maps, color paletted maps. Then when it comes to point data, you have dot maps. The analysis of these points or the distribution of points include the search for patterns and underlying processes. So point data is again somewhat confusing. Say for example, if you have now I have set of points, right? I have set of points. Now, if I draw if I draw a box like this, what can you say about these points inside? Can you see these points? It is well spread or concentrated. Are these points well spread or concentrated? Anybody?
Concentrated.
You think it is concentrated, right? I don't change any of the points. I don't change any of the points. Points are there. But I put, what can you say about the points? I didn't change any of the points. Same points are there. Now it is concentrated, right? It's not well spread. So this is not the points that we are looking at. We are looking at the boundary. From boundary perspective, we define whether this is well spread or concentrated. You see the point? So the point pattern analysis is a very difficult thing. You need to be very careful when you analyze point patterns. Right? And also, if you look at some of the values, that you have, when you look at the data, you can see the value is increasing when you go along one direction. The value is 10. Gradually, when you go towards east, it becomes 15, 20, 25, 30. Then you assume that it is increasing when you go towards east, and you give your conclusion. Right? But it can happen in a way that it is from one point, it is increasing, and then suddenly it start decreasing. And then again it increases. And again it decreases. Right? So if you look at a small portion of the data, you will make a wrong conclusion because you are looking at only this part of the process and say it's increasing. And then if you increase this, assuming that, if you assume that it is increasing like this, you are making a mistake. So if you, Gobinath, can you switch off your microphone?
Okay, sir.
Right. Okay, I muted it. Okay. So if you sample only this area, you sample this, and then make extrapolation, you will we are making a mistake. So you need to look at it very carefully when you do the process. So you need to understand pattern and underlying process for that. So dot maps, you can produce dots. Okay. So dots represent can be a process, incident, occurrence, the occurrence of plant species, location of farmhouses, location of towns, villages, cities, or even earthquake epicenters. Dot can be a crime location, location of crime, location of a crime, that also be possible. So likewise, it can be Even it can be a 3D, say farm. You can have a area of a pond, how concentration of oxygen is in the pond. So it has a length, width, and height, three-dimensional portrait of things. Can still put in a dot map in three-dimensional. And we can have network data, which involve transportation network, supply network, drainage network, water supply, electricity supply, then whatever the distribution of certain things. Where connectivity is a factor. Connectivity can be physical connectivity or can be virtual connectivity. So if you take the telecommunication structure, mobile telecommunication network, it is not physically connected, right? It's virtually connected. It's connected through signals. It's still a network data because it has a direction. It has a flow path, where to flow. Transport network, you have where it flows. And then you have directional data, which basically has angles, directions, as in the bearings. So this is a totally a different way of approaching. And if you look at the point and aerial data, there's no very clear-cut distinction between aerial data and point data. So when you have a phenomena which is spread all over the area, we call continuous data. If you look at the temperature surface of a lake, it's continuous data because we have a surface. But when you have a population density in a map, all the people are not equally spread, so it is not true. So when it is population spread all over, not uniformly, how do you assess the distribution? You have to divide aerial subdivisions. You have to go for small areas, then only it becomes representative. It becomes representative. So you can convert the point data into aerial data in spatial statistics. We use different techniques to convert point data into aerial data. We use some of the advanced techniques, but there are very basic techniques that we have borrowed from various other disciplines, like Thiessen polygon or Voronoi are borrowed from climatology. Now, first one, if you look at the Voronoi, how do we construct the Voronoi? How do you construct the Thiessen polygons? Okay. How many of you are aware of how to develop Thiessen polygons? It's a very simple thing. Right? If anybody has not heard, can you put a chat message saying that don't know or no? Put us no and send a chat message so that I can see the count. How many people are aware of Thiessen polygons? Just type no or yes, one of the two. So if you yes, you don't need to type because I can count the balance. But if you say no, and if everybody know, then I can understand. Okay, enough. Everybody is saying no. Right, okay. Right, I'll explain it. Thiessen is the name of the person. Thiessen. Thiessen is a scientist who found this. And it is constructing polygons. Some people call it as polygons, and the correct pronunciation is polygons. Right? GONS is not guns. Guns. Right? If you go to Latin America, if it is in Latin or Spanish, Italian, guns is guns. GONS is guns. And English, it's guns. So polygons, not polygons. Right? How you pronounce it. Thiessen is the name of the scientist. He used polygons to develop it. Voronoi. This is called actually Voronoi. Voronoi. But when you put it in plural, you put like polygons, Voronois. But S should not be there. We call it Voronoi diagram. And what it says is, when we identify Thiessen polygons, we identify polygons for points. For example, we have rain gauging stations, 10 rain gauging stations. What is the area each one represent? You draw a polygon. Right? And then when you have a kind of a rain gauging location, we have a rain gauging station. We have another rain gauging station. We have another rain gauging station. So each rain gauging station is having a representative area. So if we draw polygons So this has this kind of it doesn't have to be a square areas, but so likewise we have polygons which represent each rainfall. But my polygons are not actually representative, but Thiessen introduced a method to find how you can draw the polygons. So I will show you how it is done. I think I have an example. Procedure is join each point to all neighboring points, bisect these lines, draw the regions. Although we borrow this from climatology, Thiessen polygons can be applied in a variety of human behavioral analysis, such as market studies. So we will see how it can be developed. Right. So I'll show you, there are 3 points, P1, P2, and P3. Right? And then to draw Thiessen polygons, what you do is you connect these points by straight lines. Then you draw for each straight line, you draw perpendicular bisectors. You know what perpendicular means, 90 degrees to that line. Bisectors means divide into 2 sectors. Bi means 2. Bicycle is 2 wheels, 2 cycles, right? Bilateral means 2 sides, bilateral discussion, right? Bilingual, to speak 2 languages, bilingual. Even the term biscuit came from bi. Earlier, biscuits have 2 sides. You put these 2 together, in the middle we have some cream, that's a biscuit. But now you have single side biscuits as well. So bi represent 2. So you draw 2 equals, so you divide each line. If you look at the line, this line, you divide into 2 equal parts. So all 3 lines are divided by having bisectors. When you extend these bisectors, you have the areas identified by the bisectors. So you have an area for station P2. The area is from here. This is a straight line. Here boundary, then it's a straight line joining this. So that is the area. Right? So if I color that area, so this is the area occupied by station P2. this is the area occupied by station 2. So what we did was only draw, what we, to develop the Thiessen polygons, what we did was draw perpendicular bisectors, first joining the each adjoining station. Each adjoining section, we join and then we draw perpendicular bisectors, and then we extend these lines to have the, so we erase all these lines. So this is one area. The equation to calculate the average value for the area is this. P bar is average, is A is the value of the area, A1 is the area of station 1 into P1. A1 into P1, A2 into P2, A3 into P3, divide by the total area, you get the average value. Right? Now, if I give you the values and the areas, can you calculate the average value? Right, okay. I'll give you the value, set of values. Rainfall, station A, value is station A, rainfall is 10, oh sorry, 100, and area, rainfall is 100, so this is P, precipitation is 100, area is 4,000 square meters. Okay, and station, that is station A. Station B, precipitation is 200, area is 6,000. Station C, precipitation is 500, area is 10,000. Calculate average P. Can you do the calculation? Quickly. Okay, if you have finished calculation, can you put the value into a chat? Nobody has worked out it yet. Can you quickly calculate and put what the average P is for the area? Only one so far. Okay, most of you have got the answer correct. It is 330, right? Now, if I increase this value, right? If I increase this value, area, instead of 4,000, I put 4 million. Instead of 6,000, I put 6 million. Instead of 10,000, I put 10 million. Right? How do you calculate now? You again take that value, multiply, do it. Right? There's a short way of doing it, right? Now, when you have this kind of data set, you see in rainfall, you have all with double zero. You can drop this double zero for everything. You can take 1, 2, and 5. And area, you have 3 zeros common for everything. You can drop those 3 zeros. So basically 4 multiplied by 1, 2 multiplied by 6, 5 multiplied by 10. 10 plus 12 plus 4, 66. Total area is 10 plus 6 plus 4, 20. You divide 66 by 20. And then you subtract, reduce the number by 10, the rainfall. So you multiply by, 100, you multiply by 100 or add 2 zeros, what you dropped. Very simple. Right? So when you have large values, you can drop those values and calculate. Now, what I will do is I will erase this. Right. And I will undo some these lines. Now instead of right, I reduce. Now I have an additional point. Here. You can see it, right? I have an additional point here. Right? We have additional point here. Now, if you draw the Thesan polygons, what will happen? So you draw Thesan polygons now from here to here, 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 and here to here. Right? And then if you draw the bisectors, right? Now you have 4 areas. We have 4 stations, 4 areas. 1, 2, 3, and one small area in the middle. So I will increase the thickness of the line. Now I have four areas. Middle, I have a small area as well. Right? Middle, I have small areas. Now, if I know the area and the rainfall in the middle, can I calculate the average? You can. Now, by having a new point in the middle, what has happened? Earlier, we had only P1, P2, and P3. Now we have additional point. So additional point has got some area. Who has lost? All P1, P2, and P3 have lost some areas. So if you look at the area, small area is lost by station P2. Right? P2 lost small area. P1 is also lost small area. Right? And P3 also lost a small area. And the fourth one, new one, gain some area from all four. So if I erase this and now, if I so when you have additional area, new location, data, what you get is other stations will lose some areas. And the new one will gain areas from other stations. Same thing with like three hospitals are there. P1, P2, and P3 are the hospitals. If you have a new hospital here, what will happen? P1 will lose some patients, P2 will lose some patients, P3 will lose some patients, and the new one will get some patients from all three. So this is the theory behind the Thiessen polygons. If you have the points, you can calculate the effective area by drawing Thiessen polygons. If you add new points, what happens is new points will gain some area, other points will lose area. Depending on where you have the new point, suppose you have the point, new point here. Suppose you have a new point here. Then you will find that you will not lose any areas from P3. Right? Now what you do is you connect this with lines. So you connect these stations with lines. and draw bisectors. And then if you delete these lines, you will find the Thiessen polygon areas now. Right? So new point will not gain any area from P3 because it is far apart. So the law of similar things are together applies here also. If it is far, it does not contribute any area for the new station. Okay. Now, this is the theory again we use to develop or to get new values at any unmeasured points. Right? I'll explain how it is done. Now, if you have only three stations, P1, P2, and P3, right? And so P4 is no longer there. P1, P2, and P3. And then you develop Thiessen polygons. Okay? You develop Thiessen polygons where P1 rainfall is 100, P2 rainfall is 200, P3 rainfall is 500, P1 area is 4,000, P2 area is 6,000, P3 area is 10,000. Okay? So you know how to calculate. You calculate some value of 330 average value for the area. Right? Average value for the area. Now we have four stations. A new station, and now we have drawn the Thiessen polygons. Right? Now, the P4 precipitation is 250. Right? If the P4 precipitation is 250, and if the area for P4, you said this area belongs to P4, but that is taken from P1 and P2. So P1 lost, say for example, P1 lost 400 units, and P2 lost 600, right? Because this area was taken from P1 and P2. So if this lost this 400 and 600, so now the new area is P4 is having area of 600 plus 400, 1000, right? 1000. If you calculate the average now, will it be different? Yes, because P is different. So station A will have area of 4,000 minus 400, right? This one is area now is 400 minus 4,000 minus 400. P2 area is 6,000 minus 600. P3 area is 10,000. Now you can calculate the average. Now you can calculate the average and see how it is different, right? So this is basically a Thiessen polygon. The Thiessen polygons, you can lose points, you can gain points. In this case, we gain one new point, P4. So now earlier you calculated the average rainfall, P bar is 3. You can calculate what is the P bar. And see the difference. So when the new points come, now if you have new points everywhere, right? You are going to have new points everywhere. Now what will happen? You will extract this data for the new points from the known points. So if you have another point here, another point here, how? So I'll give you a small exercise. This Thiessen polygon, use a catchment with 4 stations. You can do it on a graph paper, mark it, count number of small squares and then calculate the area. So use a catchment with 4 stations. Assume some rainfall values. Okay, since we need to get one answer, I'll give you the values for stations. So station 1, rainfall is 240, area is 3,600. ST2, rainfall is 300, area is 2,500. Station 3, rainfall is 400, area is 3,000, and Station 4. Rainfall is 600. Area is 100,000. Okay. So draw a Cartesian polygon and calculate the average, and then add two at one point and with at one point with rainfall of 500 at one point of another point somewhere with 500, which has the areas coming from these three. So this will lose 200 units. This will lose 300 units of area, and this will lose 100 units of the area. So if we have 4 stations having rainfall 240, 300, 400 and 600, and we have 4 areas having 3,600, 2,500, 3,000 and 1,000, and we add new points with rainfall 500, and that new station is form of 200 from station 1, 300 from station 2, 100 from station 3. So I'll simply double this area, 4, 6, 2, right. And then new point having rainfall 500, calculate the average rainfall now. So first calculate the original data, 4 stations, what is the average, then add new point, calculate the average. Okay, any questions? Okay. I'll wind up the session if you don't have any questions. Have you got any questions? So work out this and draw the figure also on a piece of graph paper and or even normal paper, and then calculate it and be ready to show it at the next class. Okay, so I'll wind up the session now, and so I'll stop sharing, and um, so I will give you the summary of the lecture in the chat. I'll send you the um, so today the topics that we discussed are the ones I type here. So okay. Right. So we'll wind up the session now.